Hi everyone, my name is Hoa Van Nguyen. Today I will present our work entitled LAVAPilot, Lightweight UAV Trajectory Planner with Situational Awareness for Embedded Autonomy to Track and Locate Radar Tags. We are a team from the University of Adelaide working on autonomous systems research with a focus on using drones for multi-target tracking. Recent studies have shown that the wildlife extinction rate has been alarmingly high, and more than half of mammals, birds, fish population has dropped by half in only 50 years. To preserve the wildlife population, conservation biologists have a strong interest in understanding animal behaviors, how animals use their habitat, what are their movements and activities, how they interact with each other. To study animal behaviors, biologists have been using radio telemetry since 1950s to find the animal locations. The two most common types are GPS and VHF. GPS tags are excellent for localizing animals given the location information is directly available. However, it is by no means the perfect solution for all scenarios. GPS tags have short battery life and its weight and size, making it not applicable for tracking small animals, and its high cost also limits the ability to mass deploy. In contrast, VHF-based radio tags do not provide location data directly, thus making it difficult to localize. But it is significantly cheaper, robust, can be fitted from small insects to large mammals, making it the most important and commonly used technology nowadays. How people do tracking nowadays? You can see in the above photos. Most biologists need to track in a long distance in a remote area with a cumbersome VHF radar antenna, a handheld radar receiver, and manually home in animal locations based on signals emitted from color tags. Sometimes they need to climb on tree or hide an aeroplane because the terrain is inaccessible. With the recent development of UAV that make drones getting cheaper, portable, and can fly anywhere, this development helps to open new possibilities that we can use drones to track animals. Let's take a look at our problem. First, the wildlife are attached a VHF radar tag, wherein each tag transmits a low-power on-off key signal every 10 period. As shown in this picture, we assume that the objects are detected by the onboard antenna of the UAV and the total numbers of objects is known. Furthermore, to minimize the disturbances to wildlife, the UAV must maintain a safe distance while tracking them. For the background, the online target tracking and localization systems generally consisted of two parts. The first is the state estimator, or so-called tracker, to estimate the target state. And the second is the planner, which to compute control actions that maximize a certain reward or minimize a certain cost. For the multiple object tracking, the objective is to estimate the target state such as position and velocity. However, there are several challenges such as noisy measurements, false alarms, and misdetections. For online planning, the common objective is to compute an optimal control action that improves the localization accuracy, which is an NP-hard problem. Further, the object states is not observable and there is uncertainty of future target states and measurements. For our motivations, first, we want to automate the cumbersome task of localizing radar tag wildlife for conservation biologists so that they don't have to climb a tree anymore. Second, We want to remove the need for a cumbersome ground control system in the loop by developing a portable and fully autonomous system onboard tracking and planning algorithms. Third, we want to minimize the potential disturbances from drones to wildlife during tracking and localizing tasks by maintaining a safe distance while flying at a low altitude to conserve battery. The early work into demonstrates the using of a UAV for successful real-time localization of a stationary live bird. Here, the UAV performs a full rotation to produce bearing measurements. Since the object is stationary, they use a grid-based filter. Although the bearing-only approach is robust to different terrain conditions, it also has a lot of drawbacks. The receiver system is complex and heavy, which will affect the flight time significantly. Further, it requires a very slow measurement wherein each measurement takes 45 seconds to complete, which is not applicable to track mobile objects, as confirmed by poor localization results for tracking a live bird. Another approach is proposed in our previous work using RSSI-based method, which is fast and accurate using particle filter, with the average accuracy is below 25 meters. Hence, we consider RSSI-based measurements since it provides fast and reliable results, and we use the particle filter to track wildlife. However, all of the previous work consider the computational demanding information-based path planning. In contrast, we are seeking to realize a lightweight and real-time planning algorithm that can embed it on the onboard low-cost drone platform. Therefore, we propose the first fully autonomous system to track radio tag objects, wherein the control action is computed on board using a Raspberry Pi. For our approach, we developed a lightweight task-based planning method called LAVAPilot, which is, first, move toward to the object with the lowest position estimation uncertainty, and second, maintain a safe distance to the targets of interest. First, let's take a look at our simulation results. Figure 1 shows the UAV's trajectory heat map using LAVAPilot over 100 Monte Carlo trials, where A is the route to, B is the heat map under the void constraint, and C is the heat map without void. The results show that LAVAPilot successfully maintained safe distance to all of the targets when using the void constraints as shown in Figure B. Further, as shown in Table 1 and 2, LAVAPilot performed as well as the information-based methods in terms of localization accuracy, but with over 98.5% reduction in computational cost, although with a 17% increase in flight time. For the field experiment setup, we use VHF animal collars used for tagging and monitoring the endangered southern hairy-nosed wombats for our experiments. Here is the location of 4 radar tags at our test site, when the star denotes the UAV starting location. Let's take a look at our field experiment demo, where the left-hand side shows the LAVAPilot without void, and the right-hand side shows the LAVAPilot with void. The results show that our LAVAPilot algorithm can maintain a safe distance to all of objects while tracking them accurately. Note that the void is not violated in this case, since the particle distribution is multimodal, as shown in this figure. When the task completes, the UAV takes the shortest path at 80 meters AGL to minimize disturbances to localized objects. After that, the UAV will be landing off to finish. Here, take a look more at our few experimental results. Figure 2 shows a few trial missions to localize for stationary tasks. Here, stationary tasks are used to ensure a fair comparison between with void and without void strategies. The results confirm that our tracking algorithm can localize for radial tasks accurately, and there is no significant localization accuracy difference between the two investigated planning methods. Figure 3 shows the estimation uncertainty over time for all four targets, while table 3 depicts the localization performance over 6 field missions. The results further confirm the effectiveness of our proposed algorithm, and there are no significant performance difference between void and without void methods. In conclusion, a novel planning method is realized in an energy and computation-limited platform. We use a situational awareness algorithm to maintain a safe distance from objects during trajectory planning. Simulation and field experiments with multiple vehicle radar tasks demonstrate the capabilities of our system. We have also released a full source code in the paper or showing the below QR code. There are three potential directions to extend the current work. First, we can extend the current system to multi-UAV system. Second, we want to conduct field trials to track the real wombats. Third, we may implement other filtering algorithms, for example, bulk particle filter, to improve tracking accuracy and computational time. Thank you very much for your attention.